Welcome back to the lecture series in role of nanotechnology in animal production. So, in the previous class, I highlighted upon three aspects, and let's revisit those. One, there is a need for clean water, one of the major requirements of all the modern societies, whether urban or rural or wherever. Okay. For industrial application, agricultural and drinking. And there is tremendous thrust on desalination of water so that we can use the ocean and the seas and all those resources. Second area where there is tremendous thrust is the garbage or organic waste disposal, converting them into useful materials. Similarly, I gave you an example from the DRDO, Government of India, where human feces are being converted into water and some form of carbons which are benign by the use of microbes, and that is what you must have seen in terms of green toilets in trains as well as in army post in remote places. Okay. Then next I introduce the concept of multifunctional sustainable green materials. Multifunctionality in terms of a same material, say material X, having multiple functions, say agriculture, energy, waste management, water purification, electronics, likewise. Yet the material should be environmentally benign, easily degradable, and elemental composition or component should be easy, safe, acceptable, compatible with the living system. To give you an example, say for example, last I would say 70-80 years of electronics is mostly on a case study of silicon. Okay. So, especially the crystalline silicon. So, crystalline silicon, if we go back, so the journey of the silicon revolution, or especially the crystalline silicon revolution, which has revolutionized our electronic world, started with Bardeen, Britton and Shockley. Okay. Bardeen, John Bardeen and Britton and Shockley, and this was around the era of 40s, so 1940s and 50s. This completely revolutionized the world of computational electronics and hardwares. And all the computers, all the gadgets what you are using are all made up of crystalline silicon. Now, crystalline silicon comes at a cost. What are the cost in terms of rupee if you look at it? And we are talking about synthesis. It is a very processing and manufacturing of chips. These are exceptionally cost intensive process. You need pretty high quality of clean rooms, almost zero dust free clean rooms, zero particulate free clean rooms, and there are very few facilities. Like if you look at the current day, you will see chips of Intel, Motorola and maybe few others. That's it. Only handful of companies are involved in manufacturing these chips for all the electronics application. But then the next problem is how to the handling electronic waste. Think of it. You in your lifetime use at least, with the current estimate I see, people do not use a cell phone more than 2 years or 3 years. Okay, that's kind of stretching it. So each one of us are consuming some basket full of cell phones. They have to be dumped, they have to be destroyed, they have to be refurbished. How we do so? The electronic waste. I mean, look around, computers, huge screen, huge monitors, this has to be dumped. Where are we dumping them? Manufacturing world, the world of industry, the world of modern day living, all the huge gadgets what we are using, where are we going to dump them? And if you think, even if you give 1 minute of your whole day, you will realize that this is one serious problem which is going to haunt us in decades and centuries to come. How to really destroy them? How to ensure that all those extraordinarily kind of material what we have used, like crystalline silicons and several others, they will get degraded and will become part of nature. Well, we all enjoy to use all of them, but that's where the future lies. What kind of machines are we talking about? What kind of, because even if you look at the size of the transistors, they cannot go down beyond a point. If you follow, those of you are interested in following how the size is getting decreased and the aspect ratio is getting decreased, and follow the Moore's law, there's a limit, there's a physical limit up to which you go. Beyond that, you will have quantum tunneling effects and all other tricky things which will come into play. There are, of course, emerging fields like spinotronics and others, where people are talking about using the spin signature for computation. Yet there is another area which is also popping up. It's called DNA-based computation. Though it's in its very infancy, thinking of computation. So let's do a comparison for a minute, since most of you have some knowledge of biology. Now, if this is where all our electronics and computer world is, so where is our inspiration to look at it, to counter this? So to counter this, our inspiration is here. A neural circuit, a brain circuit. Brain circuit does the same thing as what a computer does, okay, but it does in a very different way, and it uses simple neurons to do the computation. Unlike those chips which needed these kind of extraordinarily tough settings to be manufactured, biology does it in a very simple way. Or if this is one example for us to look, the next example for us to look is how nature split water. This aspect is again very important for us to appreciate that for energy there is tremendous thrust on hydrogen, one of the cleanest form of energy. But then what could be the major source of hydrogen? It will be water. if you could split water into hydrogen and oxygen, you can use this hydrogen for energy. And how nature does it? Nature split this water in photosynthetic assembly. In other words, this process, nature does actually a photocatalysis. But nature's photocatalysis is being orchestrated in photosynthesis. If we look at photosynthesis, this water splitting is being orchestrated by something called manganese cluster. So, those of you are aware of it, there is something called a Z scheme of electron transport. Okay. So, there are these two photosystems sitting at different redox potential. Photosystem, say I call it A, I call it photosystem B. Now, both photosystem upon receiving light energy h nu excites an electron, and both these electrons, so on my left hand side, if I put the reduction potential or redox potential scale. Okay. Now, both these electrons which are emerged out are having a different reduction potential. So, these electron, after climbing, hops back and does a lot of reduction process. Okay. We'll come to that in a second. Okay. And if you look at the reaction of photosynthesis, it is this reaction. Oxygen as a byproduct coming out and carbohydrates. Okay. So, what essentially happens is this. In this process, through 100 years of study, people realize that it is the water which is splitting up into oxygen, one product, and this hydrogen comes here. So, this, when it is getting split up, so there is an oxidation which is happening, you are losing the hydrogen, and this hydrogen comes and reduce this carbon dioxide to generate carbohydrates, the food. Okay. So, this process out here is the reduction process which is happening. So, CO2 plus going for carbohydrate. So, I am not doing it by stoichiometry, but this is what is precisely happening. But then what is out here? So, this part, if you look at photosynthesis, so this aspect of photosynthesis is the light reaction. And the other half of photosynthesis is the dark reaction, or where you have the Kelvin cycle and all other things which are taking place. Now, photosystem 1 excites one electron, and this electron traveling, reducing, and eventually, whereas photosystem, the other photosystem also excites an electron. So, once both of them generates an electron, they are devoid of their minus electron. Okay. Now, they will almost behave like free radical. Now, they have to be brought back to their ground state. They are being brought back by their ground state when photosystem B supplies it electron, it hops through and brings photosystem A to its ground state. Fine, no issues. But what will happen? What will be the fate of this photosystem, which has donated its electron through a very cascadey way to photosystem 1. So, the electron has been donated here. Now, by the way, just for your understanding, this electron which goes, it reduces, there are intermediate which are here. I am not getting into those intermediates. So, essentially when we say this electron reduces this, it does not mean that there is a single electron which is moving. It is basically there are complexes which are getting reduced based on their reduction potential. Okay. Now, who is going to bring this oxidized photosystem, or in this case what we have labeled it as photosystem B, back in its original shape? Okay. So, now that is being brought by, so it needs an electron. This electron, it gets just underneath it, there is a small cluster sitting, and this cluster is called, what I was telling you is manganese cluster. Manganese cluster is a very interesting structure. So, there are, as of now understood, 4 different manganese sitting at different oxidation state. So, manganese could have multiple oxidation state, as you know. It could have 2, 4, 6 likewise. Okay. So, this manganese, these different manganese which are sitting there are sitting at different oxidation state, and their oxidation state cannot be changed. Okay. They only could fluctuate as if like a two-way switch, you know. They can move, say, +1, -1, +1, -1, depending on what state they are. And it is very poorly understood that when a water molecule gets trapped into this state, and what it does is it splits that water molecule by oxidation reduction relay to oxygen and generates the reducing force in the form of protons, or in the forms of hydrogen. Okay. So, I will close in here. We will continue from here our journey of how these are going to inspire the next generation of nanomaterials. Thank you.